All right, so we said that towards the end of the course, we'll integrate the various blocks that we have learned and make an op-amp. So let's start today and see how this particular op-amp can be constructed here. All right, so the operational amplifier that I'm going to talk about would be a very simple op-amp. And so let me skip this particular part here. So the specifications of our op-amp are that it's a very modest op-amp, as you can see here. All that we are trying to do is build an op-amp with a gain of 1000. A reasonable op-amp would have gain of 10,000 at least, but that would require more effort and more number of lectures. And since we are short on time, so we'll build a modest op-amp, which is 10 to the power 3. Okay. Input resistance of 100K. Again, a 741 op-amp will give you in mega ohms. Output resistance of 100 ohms. A good op-amp may give you 10 ohms. So all these specifications have been scaled down. Gain has been scaled down. Input resistance has been scaled down. Output resistance also has been this thing here. Okay. All right. So supply voltage for us is plus minus 12 volt. And a further simplification I would make is that I'm not going to use any active load. I'm going to build an initial op-amp. So this is the first level of op-amp, and I'm not going to use active load, just work on where the loads are passive resistors. Okay? And because I require a gain of 1000, so a single stage amplifier will obviously not be enough. So at least you would see that I would require 3 broad stages. So the first one will try and get the input resistance through the first one. Input resistance of 100K, so that will give us the input resistance here. And we are going to build an op-amp monolithically on a piece of silicon. So the first, so we are not going to use any capacitors. So the first stage has to be a differential pair. Okay. All right. So a differential pair with a high input resistance is what we'll do. So we require a gain of 1000. We don't have enough. We will not get enough gain from stage number 1. So we'll have to use another gain stage, another common emitter amplifier to give us further gain and boost it up to 1000 here. And once we try to, you must have seen that once you try to build up high gain, you invariably, gain depends on GM-RC. So invariably you end up using large RC, large collector resistances. And therefore you will not be able to get the output resistance here. So we have to add a stage here, and we'll do some stage here, common collector stage here, which will lower the output resistance to 100 ohms here. All right, so that is the strategy here. So let's diff amp, common emitter, and common collector amplifiers. All right, so let's start with our differential pair. So first stage is a differential pair, and we know how to realize this current source through a transistor, so I'm not going to bother with it. We know how to do this here. So this is the differential pair, and in yellow over here, I'll write the specs of the op-amp. This is what we are trying to achieve. Okay. All right. So first thing is, note that while the gain can be realized, part of it by other stage also, the input resistance has to be realized by the first stage only. Okay. So first stage has to give us the input resistance. So we start with Rn. We start with Rn. Rn is 2R pi. So when I write here input resistance, I mean a differential input resistance. So Rn is 2R pi, which is 2 Vt by ICQ1 times beta is 10 to the power 5. And from here we get IEE here, which is twice ICQ1 is 0.1 milliamperes. All right. So the first thing we do is we try to satisfy these specs regarding the input resistance here. And for that, we know that if we choose IE to be 0.1 milliampere, at least the input resistance is satisfied. I don't need to bother. So I'm not going to change this current anymore. I know that beta is 100, and therefore this current is fixed to 0.1 milliampere. Now the thing is, what about RC? All right. So the current is fixed here. What about RC? How do I choose RC? Well, remember, gain requirement is pretty high. So one of the strategies could be, let me try and get as much gain as possible from the first stage. Okay. which means if you recall, gain, differential mode gain 0.5 GMRC is 0.5 ICQ1 RC by VT. So if you try to build up high enough gain, what you're going to do is require a large value of ICQ1 RC, large drop here. Okay. Now the issue is how large a drop can I get? This is what decides the gain here. How much drop do you build here? So how large a gain can I get here? Now note that this value, when I do DC analysis, this is 0, 0 here. This voltage is minus 0.7. Minus 0.7, and I have to keep the transistors in active mode. Right? So I have to maintain a sufficient VCE. And so let's say, we are saying that you need more than 0.2, but you have 0.2 is just at the edge of threshold. Okay. So this is a little bit arbitrary, but let's say I keep at least 1 volt here VCE. Well, you could have chosen 0.7 also. So those choices can vary. So I'm choosing here at least 1 volt here VCE, which means that if this is minus 0.7, then this point has to be 0.3. Okay. 1 volt I'm keeping to maintain the transistors in active mode. So this is 0.3, which leaves us with a drop of 12 minus 0.3, which is 11.7. And if I put 11.7 by VT times 0.5, I get a gain of 227. So I can, if I choose, and accordingly, note that I already know the collector current here, because this current is 0.1. I already know the collector current here, and therefore 12 minus 0.3 divided by the collector current will give me the resistance. So I get a design that I should choose RC equal to 227K. And if I do that, currents have been already chosen, and I may get a gain of 227 from the first stage. Okay. So first stage may give you that. But obviously we need a gain of 1000. So we need another stage which will give us gain here. All right. So this is our first stage design. 0.1, 227K, 227K. If I choose it like this voltage DC value will turn out to be 0.3. All right. We have to add another stage. So let's see this particular stage here. Let's try this particular stage which is a common emitter amplifier with RC2 here and with RE2 here. All right. Now, when we normally do a common emitter, we say, well, here is the source and here is the load. But our source now for this common emitter amplifier would be the previous stage. All right. So let's connect them up. Okay. Let's connect a common emitter amplifier with here. Now you will realize why am I keeping RE2? If you're wondering why RE2, note that what was the voltage here? 0.3. The voltage here was 0.3. The voltage at this particular point is minus 12. If you don't keep RE 0.3 here and you directly connect it here, what will you get? Minus 12 and 0.3. How can you have a forward bias like that? You can't have. All right. So you need a place where to drop the voltage here. This is minus 12 here. All right. So I need to have RE2. I can't simply take a usual common emitter amplifier, just connect it up here and with this connected to ground. I can't do that. I have to have an RE2. And note that RE2 is what decides the bias of my transistor Q2. The Q2 has to be biased, and the emitter resistance, by now you would have seen emitter resistance, the voltage at this emitter point here, and this decides how much current flows in RE2. Alright, so let's say we try out a common emitter amplifier like this. Okay, now note that this is 0.3, and alright, so what I'm going to do is, I'm not going to bother about this left half here, only show you a part of the circuit, this half here. This design is done, and so we want to focus on this. How to choose RC2, how to choose RE2, and how much gain can we get here. Alright, so let's look at that. Okay, so this is a part of the circuit, this is 0.3. So if this is 0.3, now note that the gain of the second stage, AV2, gain of the second stage is GM2 RC2 divided by 1 plus GM2 RE2. We've already seen whenever you have an unbypassed capacitor, this is the gain that you get here. And you can very quickly, you'll see it that these terms are much larger. GM2 RC2 and GM2 RE2 will turn out to be much larger than 1. Okay, which means that 1 you can neglect here, and then GM2 cancels, and you get RC2 by RE2. Practically the gain. Okay. Now also note that this RC2 by RE2 I can multiply by ICQ2 here and multiply by ICQ2 here. So effectively the gain turns out to be how much is the voltage drop here divided by how much is the voltage drop here. That's what the gain is. Okay. Delta VC is the drop here and delta VE is the drop here. Okay. So it's the ratio of the two drops. Now, this is where you see now. This is 0.3. Okay. This will be, can you see there's a 0.7 volt drop. So this would be minus 0.4. All right. This would be minus 0.4. So can you see the drop from here to here? Drop from here to here would be 11.6. Right? The drop, delta VE is 11.6. Minus 0.4, minus 12. So the drop is 11.6. Now, you want high gain. So what should you try to do? Make delta VC as large as possible. How do I make delta VC as large as possible? By making this point as low as possible. How low can I go? I need to maintain Q2 in active mode. So let's say I push it to 0. If I push it to 0, I get 4.4 volt just at the edge of threshold, 5.4 volt, and the drop here then will become 12. So what is the gain that I get? 12 divided by 11.6. I don't get any gain. I'm looking for a gain, and now I've shown you that if I use a transistor like this, common emitter, I don't get any gain. 12 by 11.6. All right? Negligible gain. Now, if you're thinking, can I change the bias of my first stage? Well, first stage, what can you do? You've already at 0.3. What is the possibility of this particular node? You can push it up. Instead of 0.3, maybe you can go to 1. I can't go low. Because if I go lower, then this transistor will go into saturation. So I can push it up. But note that if instead of 0.3, if you make it 1 volt, what will it do to this? What will it do? 1 volt. So what will it do here? It will become 0.3 and this drop will increase and it's not going to help you. Delta V is not going to help you. Delta V is increasing. All right. Plus, if you increase this voltage will increase, the drop here will decrease. So there's nothing that you can do. If you are thinking that maybe alter the bias here, there's nothing that you can do to build up gain here in the second stage. The gain in the second stage is 12, 11.6. That's it. So practically 1. So it's useless for us. Okay. At this stage, then you say, well, I've used a NPN common emitter amplifier. What if I try a PNP? Okay. Let's try that. Let's try a PNP gain stage. So NPN gain stage is not working for us. Okay. So let's try a PNP gain stage here. Note that PNP would be, RE would be here, RC would be here. Let's connect it up to our differential pair here. Okay. Let's connect it up. All right. Now note that once I connect it up, as I said earlier, so I have a differential pair, I have a gain stage common emitter, and what will happen is RC2 will be large, and we need a output resistance of 100 ohms. And therefore, we need a common collector stage here. So if I go, I may make a first, my first schematic for an op-amp may look like this here. Differential pair, gain stage, and I add here a common collector, bias it through a current source with the idea that when you look into the emitter, you'll see a small resistance. Maybe you'll get 100 ohms. We'll have to see how to design it. Okay. So this looks like, let's try and look at this particular arrangement here. Now, when I do that, remember, one of the things about an op-amp is, or any amplifier in general is, if I don't apply any input here, 0 and 0 here, I should get 0 here at the output. All right. So with that in mind, note that if I need a 0 here, the voltage here should be 0.7. Okay. I should aim that when I'm designing my second stage here, I should aim for a 0.7 volt here. So that when I don't apply anything here, the normal output voltage is 0. No input. And therefore 0 output. Okay. So with that in mind, we get 0 here. So we need 0.7 there. All right. Let's look at the design of the second stage here. So note that I've put 0.7 here. There's a reason why we have put 0.7 here. Okay. So 0.7 here. All right. We've already seen that this was 0.3. Okay. So let's look at now again, the gain of this particular stage is RC2. This RC2 divided by RE2. And so again, it's the same thing here. Delta VC by delta VE. The two drops here. All right. What is delta VC for us? Minus 0.7, minus 12. So, plus 0.7, minus 12. So the drop here is 12.7. The drop here is 12.7. And the drop here obviously will be less than 12. All right. 12.7. And note that this is 0.3. And therefore there's a 0.7 volt drop. So this is 1 volt. And the drop here then becomes 11. 12.7 by 11. Again, negligible gain. Again, we end up, so we are trying to build up gain through the next stage here. And again, we end up with a negligible gain. All right. Now, I don't have any choice. Either I can use an NPN stage or I can use a PNP stage. NPN stage, we said, would never give us gain if I connect. But PNP stage, now that you see here, suppose I change this voltage here. Suppose instead of 0.3, suppose you go to 2 volt. What will happen? Suppose instead of 0.3, you go to 2 volts. If you raise this up, what will happen to this voltage? Will go up. If I raise this up by 2 volt, this voltage will go up by 2 volt. What will happen to this drop? Will go down. And this drop, mind you, is constant. So you are seeing that I have a strategy now. If I raise this particular voltage up from 0.3 to 1 or 2 or 3 or whatever, what will happen is this voltage will go up and delta VE will go down. And I'll build up again in the second stage. But note that if I pull this up, what happens to the drop in the first stage? That reduces. So the gain of the first stage will reduce. Because note that the drop here in this is what determines the gain of the first stage here. So if I right now it is 12 minus 0.3, it is 11.7. But if I raise this voltage here, raise this value here, then the drop here will reduce, gain of the first stage will go down, and gain of the second stage will go up. Now it may happen, what I'm interested is not gain of the first stage by itself or gain of the second stage by itself. I'm interested in the product. And if the product goes up, then I'm fine. Okay? So it's not a good strategy that you take a first stage and make the highest gain. That's what you'll see. We already designed stage 1 with the highest possible gain. And then when we added a stage 2, for that design, we got no gain. Now what we are going to do is we'll make the first stage gain go down and let the gain of the second stage go up so that overall the gain will become higher here. All right. So this is the stage we are in. 0.3 here, 0.7 here, and the gain of the second stage is practically 1. All right. So now the issue is here. Let's put two of them together here. This drop here decides the first gain, AV1. And AV2 is decided by the drop here divided by drop here. Okay? Now, then if you assume that there is no loading between the two stages, that this stage does not load the second stage, meaning what? That the input resistance of this stage is much higher than RC. Then each stage is like independent in terms of gain here. So it's not affected. Then the total gain would be simply AV1 into AV2. So we'll deliberately design such that when I look right, the input resistance is much higher than RC. And then it will be simply AV1 into AV2 here. All right. This is fixed here, 12.7. Because we note that this was 0.7 here and here, so this is fixed constant here. And this is the present stage here, 0.3, a present design 0.3 here, and this was 1, and we were getting a gain earlier, a gain of 225 for the first stage here, approximately 1.15, total gain of 260. Okay? That's where we are. Now what we are saying is, we are going to compromise on the first stage gain and build up the second stage gain. Okay? Suppose I do the following. Note, go back and see how much is the drop right now? 11.7. Now I'm going to go the other extreme. I'm going to build a drop here of only 1 volt. Alright? I'm going to build a drop here of 1 volt. 1 volt means what? This voltage which was initially 0.3, I'm going to take it up to 11. Alright? So I'm really bringing down the gain of the first stage. Bringing down the gain of the first stage. But note that if I do that, if the drop here is 1 volt, then this voltage becomes 11. This voltage becomes 11.7, and the drop here becomes 0.3. Okay, drop here becomes 0.3, which means that the gain of the second stage, delta VC2 is 12.7 divided by 0.3. So I'll build up gain of the second stage here. So I'm bringing down the gain of the first stage and building the gain of the second stage here. Now note for this particular design. So what I did was the drop here became 1. Okay, so the gain of the first stage will become 0.5, 1 divided by VT, 19.2. The gain of the second stage becomes 12.7 divided by 0.3, 42.3. Overall gain becomes 814. This gain is only 225 into 260. So from 260, I went up to a gain of 814. Deliberately made my first stage gain lower, which allows me to get gain from the second stage. So we get a gain of 814. All right. Okay. So this is a choice now. It's not that this is a, now if you're wondering, maybe what I can do is perhaps bring it, make it even lower. You can play around with these things, but let's go forward. So this is now our new design is, what we are saying is that we'll design it such that this node is 11. This node is 11, so AV1 is 19.2, AV2 is 42.3 here. If this node is 11, then 12 minus 11 is the drop here, and we already know the current. The current is fixed by input resistance here. So we get a new value of RC, which is 20K. New value of RC, which is 20K. All right, so we'll put 20K here. Now, what is the value of RE2? We have not finished our design. All that we said was we chose this at 11, and this became 11.7 or so. So we got RC. So first stage design is complete now, 20K, 20K here. How do we choose RE2 and RC2? Remember what we said, that when we look from here, RN2, the resistance, input resistance should be much higher than RC. If it's much higher than RC, because whatever is connected at this point comes in parallel with RC. So we don't want the gain of the first stage to drop because of the loading of the second stage here. So we would like Rn2 to be much larger than Rc. So when you look into the base here, what do you see? You see a resistance equal to beta times Re2. Of course, you see R pi plus beta times Re2. R pi will be smaller in generally. So beta times Re2 should be much, much larger than Rc, which is 20K, which gives us beta is 100, which gives us Re2 should be much, much larger than 200 ohms. All right. So that's the constraint that we get. So let's choose something which is twice. Re2 is 2K, 10 times higher than this. So once we choose Re2 equal to 2K, Re2 equal to 2K, then we get Rc2 also. Because once you get Re2, note that once you get Re2, you get the current here. Because this, if this is 11, this is 11.7, and once you choose Re2, this is 12, you get the current here, the same current flows here, and we knew the drop here was 0.7, so you get a value of Rc2, which is 84.7. Alright, so that's how we arrive at the design of the second stage. But remember, overall gain was what? Some 800 something. We're still not at 1000. Our limit is 1000, so we've not achieved 1000, okay? But let's go forward. If you want, you can see, let's see if the simulator is working. So let's see our design. Alright, this is our design so far. Okay, 20K, 84.7, 2K. Alright. Alright, so what do we do with the design? Remember what we said was the value at this particular node should be how much? At this point? 0.7. Why? Because we are going to connect an output stage, which is a common collector, and so that the output was 0. So let's do the dynamic DC here, and let's see what is the biasing here. Our biasing is disturbed. It's 3.373. It's not really 0. That's the first problem. Okay, it's 3.3 here. But let's see what is the gain and all that. Let's see dynamic DC here. So if I want gain, note that what I need to do is go here, look at this particular node, V8. Gain is at this point, V8. So one of the ways in which you can check gain is you can do transfer function. Look at V8. V8 divided by VID Our gain is 670. The gain is 671. And input resistance is 115K, which is fine. 100K is what we need. Output resistance is 82.9, basically this value here. So this is where we are right now. All right, short of 670. Now, what has happened is we had built for 800, and in that 800 we had still made approximations. Okay, one of the approximation was that this stage does not load this one. We had only chosen a factor of 10. Factor of 10 means at least a 10% loss will be there. Okay, 10% loss will be there. Plus there are other approximations, as a result of which we are only at 670. Okay, all right. So where do we go from here? All right, so this is where we are. Expected gain was 814, and the gain is 671. Rn was here, R0 is here, 82.9. That's where we are. All right, this is fine. Note that the gain of the first stage is 671, 17.3 into 38.8. Okay. Let's add the second stage. We know that we are not at a place where we have adequate gain. 671 is not adequate at present. Okay. But let's add the second stage, the third stage itself, which is a common collector amplifier. Because, you know, when we start optimizing, the last stage would also affect what happens to the second stage and all that here. So our output stage is a common collector. A better output stage would be a class AB amplifier. But to keep things simple, so I'm adding a common collector amplifier here, biased by a current source. Again, assuming that we know how to implement this current source here. Now, the value of the current source we've already seen. So first thing is I need to keep it to 0. Output here 0, fine. The current source gives better swing, we know that. So what value of current do I use here depends on how much load are you going to drive. Because remember, we wanted a swing. Swing depends on the current here and the load here. So suppose you're looking for, when this is VCC and VE, suppose I'm looking for plus minus 10 volt swing. If the supply voltage is 12 and minus 12, a good design would be where the swing can approach the positive supply and on the negative side can approach the negative supply here. So I've not put here very close 11 something. I've just put a slightly modest value, which is plus minus 10 here. If I do that, note that the value of IE3 should be at least 10 milliamps. For swing, if you recall, swing is nothing but IE3 times RL. So for us, minimum value of RL is 1K. I'm not going to connect anything smaller than that to my op-amp. If you connect smaller than that, then there's a problem. Then I'll have to use a larger value of IE3. So right now I'm saying I'm designing my op-amp for applications where RL will be larger than 1K. Okay? If you want for less than 1K, then appropriately one may have to do something else here. So IE3 is required 10 milliamperes. So I'm just going to use 10 milliamperes here, output. So this is what my first op-amp looks like. 0.1 milliamperes here, 20K here, 2K, 84.7 and 10 milliamperes. At least it's a complete schematic, except for the realization of the current source here. All right, so it's a complete op-amp. So let's simulate the op-amp and see what happens here. Let me open this up. All right, so this is our op-amp. Okay. Complete op-amp, so let's do a DC, dynamic DC here. All right, first problem. This voltage is, we wanted 0, it's minus 4.4. All right, minus 4.4. So we have a problem. Why? Because note that when I added the second stage, what happened was second stage is, last stage is biased at 10 milliampere. 10 milliampere, which means how much base current will it draw? 10 divided by 100, which is 0.1. And if I look at my first stage, this stage is biased at what? We can see the currents here. Can you see the current coming here? How much is it? 0.18. So 0.18 comes from here, and this one requires roughly 0.1. So my third stage is drawing current and is upsetting the bias. We didn't take that into account. We said, well, let's design a common collector amplifier, put it to the second stage here. Now, when you do that, the third stage, which is biased at pretty high current, 10 milliamperes, is drawing a lot of current and upsetting everything. Okay? So what shall we do? So, well, at this stage, what we can do is we can go back and look at all the currents and all that we have, because remember, we want this to be 0. We want this to be 0 here. So now, instead of going back, now you have simulator as a tool. So first pass of design we have done. Not very good design. Now we are simulating it. We have the numbers before you. Let's do a little bit of tuning. Let's tune the design using the simulator itself. So I want this to be 0. All right. And this is minus 3.7. What do you think? Can I change this resistor and make it to be 0.7? I want it to be 0.7. What do I do to this resistor? Note that this is connected to the negative power supply here. So if I increase the value of the resistor, do you see that this value will become more positive? Does everybody see? This node is connected through the negative power supply through the resistor here. If I increase the value of the resistor, the negative power supply should have less effect on the node here. And therefore this voltage should become more positive. So let's put here some value here. Let's put some 100. Let's check. Minus 2.3. Fine. We want what? 0.7 here. So let's put 130. Well, that became too high. So let's put here 120. No, how much do we want here? We want plus 0.7 here. 135. Let's see. Close. Maybe 137. Okay, reasonable. 137. Reasonable value. Give us. So I'm using the simulator to tune. One can do it with the paper and pen and all that, but it will take you more time. All right, taking into account all the bias currents and all that. So we use 137K and we got 0, roughly 0. Now another benefit, did you see what I got? I increased the value of the resistor here. What is the gain of the second stage? The drop here divided by the drop here. So after tuning, let's look at the gain here. Analysis. Let's do the let's first of all look at the output voltage here. Our output node is number 10. So let's do analysis. Transfer function number 10. Node number 10 divided by here. Well, we got 972. All right, very close. We want 1000. We got 972. This one is fine. Input resistance will remain fine because it depends on the input current here. Output resistance is 1000 ohms. Output resistance is 1000 ohms. I want 100 ohms. Why is it 1000 ohms? Well, let's go back to our this thing here. So this is our amplifier. As I said, this is what we get, AV637. And after tuning, this is what we end up here. All right, we get 1000 ohms. Why are we getting 1000 ohms? Resistance looking from here. Why do you think we are getting 1000 ohms? Now remember what is when you look into the emitter of the circuit, emitter of the amplifier, how much output resistance do you get? R pi plus RS divided by beta. What is RS for this particular stage here? What is RS for this particular stage? Where is the signal to common collector coming from? From here, right? What is RS? 137K. When you take 137K and divide by beta, what do you get? Beta of 100, what do you get? 1.3. Right? You get 1.3, so there's a problem. This resistor is too large. This resistor is too large, and that's why it's giving me a high value of output resistance. I want 100 ohms. So what do we do? Well, if you want, now you start from here. If you want 100 ohms, how large a value can I use here? If you neglect the value of R pi by beta, which is small, how large a value should I use here? Instead of 137K, maybe if I use 10K, 10K divided by 100 will give you 100 ohms. So if I use 10K here, then note that the gain of this amplifier depends on this resistance divided by this resistance, because the currents are the same. So if I use it to 10K, I'll have to reduce this also. I'll have to reduce it to 146 by the same factor to maintain the gain of this stage here. Now note that if I reduce that, do that, what will happen? Remember, input resistance from here was what? Depending on this value here. Input resistance will go down by a factor of 10 or so. This will start loading this one. And will pull the gain of this stage down. We are already only at 972. Right? So what do we do? Rn2 would reduce. Alright, so for example, let me show you. This is, again, when I simply did 10K and 0.146K, the biasing also got affected. The biasing got affected and my gain became 513. The gain of the first stage collapsed from 19 to 9 because it got loaded. And output resistance came out very nice, 84 ohms. Input resistance is also fine. So what do we do? Do we know what? So I remember when I look from here, if I don't want to touch this now, 84 ohms, because I have to get 100 ohms. Okay. So this is 10K. Then this has to be small. But then what is happening is this stage is getting loaded by this particular stage here. Can you prevent loading such that this stage does not get loaded by this stage here? How do you prevent loading? To prevent loading of first stage here, add a common collector intermediate stage here. Common collector does what? Common collector provides you with a high input impedance. So what we're going to do is between these two, add a common collector here. Add a common collector stage here. Okay. Now what this will do is, note that when my first stage looks into it, it will see a high value of resistance here. So it will not get loaded. And Q3 and all that, I'll still design it in the same manner. Now maybe I'll get it. Okay. By the way, this, I don't know why this does it. The current sources are supposed to be down. Here, current sources are up. Okay. So keep in mind, this is all down here. All right. Okay. So this is our design now. AV3 is RC3 by RE3. So again, let's start from here. We want 0 volt here. We want 0 volt here. So the voltage here will be 0.7. And so look at this. VE3 we are setting at 11.7. AV3 we are setting this value at 11.7 here. Remember earlier it was 0.3 volt here. So same thing, 11.7 here. Yeah. And so our AV3 becomes 42.3, RE3 becomes 236. Can everybody see? 0 here, 0.7. This I'm keeping at 10K to keep output resistance. So current here is decided. And I chose a value of 11.7 here at this particular node, which is what we had chosen earlier also. And that decides how much is RE3 and then we get a gain of 42.3. So this is 11.7 here. If this is 11.7, this is 11. Okay. And this becomes 10.3. The current is already decided here. So that gives us the value of RC, 34K. And the gain of the first stage becomes 32.7. The next thing is 32.7. Now I don't want this stage to load. So beta RE2 must be much, much larger than RC. Beta RE2 now, not RE3. Must be larger than 34K. RE2 must be much, much larger than 340 ohms. That gives us RE2 at least 3.4K. Alright, so this becomes our design then. Value of RC we know 34K. Value of RE2, RE3, RC3, everything done. Okay. So when I simulate it, again what I find is some biasing is 1.2 here and 1.97. But gain I get 1000, more than 1000. Input resistance 115K. Output resistance 90.86. Well, we have all the right values except for 1.2 here. I want 0. So a little bit of tuning. If I tune this, this value here instead of 10K to 9.1K, now I get 0 and gain of 1002, 115 and 82.2K. Just barely made it. Okay. Barely made it to a gain of 1000. 1002, Rin of 115K and 82.2K. So this is a final design. Final design of our op-amp. 34K here, 34K here, 3.4, 236 ohms, 9.1, 10 milliamperes. Will give us a gain of 1000. Will give us a gain of 1000. Give us an input resistance, give us an output resistance. But the design is not complete. The design is not over yet, because remember, what are you going to do with this op-amp? You'll take this op-amp. Now, let's say this is your 741 op-amp, and you're going to make an amplifier, right? Now, this is where your second course comes into picture here, E250. When I take this particular amplifier, and I start making amplifiers, right? One of the op-amp stages that you know is a buffer and inverting amplifier. The moment I put negative feedback, this stage will become unstable. This stage that you see here will become unstable. And now comes E250. You're reading a lot about it. Stability. How do I make my op-amp stable? All right. So that's the purpose of the next stage here is. So see how our op-amp has evolved. How our design evolved. We started from here. Right? Started from here. This is what it was. We tried out a common emitter, NPN. Didn't work. Tried out PNP. This is what we got here. We added an output stage here. Didn't get enough output resistance. Modified the design here. Loading was occurring here. We added another stage here. And finally we get 1002. Rn is 115K. R0 is 82 ohms.